All right, continuing on with sedimentary rocks. Stratigraphy is the study of stratified rocks. And by stratified rocks, I just mean those layered sedimentary rocks. All right, so stratigraphy studies those layered sedimentary rocks. And because these stratified rocks cover about 75% of Earth's total surface area, it's a very good skill to have as a geologist, to be a stratigrapher. Now, remember back to the principle of lateral continuity. This tells us that sedimentary rocks are originally formed covering vast areas, so that if today we see a canyon or an eroded riverbed or something like that, and we see the same rock on both sides of that canyon, then we can assume those rocks were once connected, right? And we call connecting two different rocks through space correlation. So we talked about how we could do this in a canyon, but we could also do this anywhere that we don't have all of the information in between two different areas, right? Maybe I go to one location and I see shale. And then I get in my car and I travel 200 miles and I see shale again. Now, I might not have seen that shale on that entire car ride, right? Maybe I was listening to music, talking to my friends, whatever, I wasn't paying attention. But I could correlate those two layers and assume that they were once the same layer. And so we call that correlation, connecting those in space. Now, there are three different kinds of correlation. The first one is what we call lithograph or lithostratigraphic correlation. And this is what we've been talking about, right? So anytime I see a type of rock, such as shale, and I know the lithology of that rock, I know what minerals it's made out of, I know what texture it is, I know what color it is, and so on and so on. And I see that a very similar rock somewhere else, then I can correlate them, right? Assuming that they are the same rock layer. That's lithostratigraphic correlation. I can also do this with biostratigraphic correlation. This means that I'm starting to use the biology within the rock. Maybe I see very similar fossils, right? That's biostratigraphic correlation. Or I can do this with chronostratigraphic correlation, looking at the age of the rock, right? If I know the rocks are the exact same age, then I can also correlate them. Okay, so in this image, for example, I see limestone in this core A, and I see limestone in this core B. I can assume that they are actually connected. It's correlation. Now, what's really, really cool about this is that this lets us know how an environment has changed over time. And we can do this with what we call Walther's law. Now, Walther's law, it's a little complicated to think about, a little complex. So I'm going to walk you through it. But once you get it, it's so cool. So Walther's law deals with facies. Facies is any part of a rock body that has characteristics that can infer the depositional environment. So for example, sand with a lot of seashells in it tells me that it was formed on a shoreline, right? So that's that sand facies telling me it's a shoreline. Often you'll find mud and silt a little farther offshore, and then calcite even farther offshore, a little deeper marine. All right, so the typical sequence on a coast is sand on the beach, mud and silt in shallow water, calcite and even deeper water. Now, Walther's law states that any vertical progression of facies, remember that sand, mud and silt, calcite, can create a succession of depositional environments that are laterally juxtaposed to each other. Okay. Basically, that means that same order, the sand, mud and silt, calcite that we see horizontally will also be preserved vertically within a core. So what I mean by this, let's step through it. All right, so let's say that sea level rises and all of these facies, the shoreline facies, the shallow facies, and the deeper facies all start to shift inland as sea level rises. Okay. Now, this shifting inland is going to cause the same sequence of facies seen horizontally on the surface, which we know from the ocean to the land is calcite, mud and silt, and sand. That's going to produce the same horizontal order. So if I was to take a core, right, and look horizontally down into the seabed, the sequence that was produced, I would see that exact same sequence. From the top of the core to the bottom of the core, it would be limestone, which is made out of calcite, mudstone, which is made out of mud and silt, and sandstone, which is made out of sand. So by looking at a core, I can know, right, how this environment changed over time. If you look at a core and you see that sequence of limestone, mudstone, sandstone, you know that the sea level rose and that all of those environments shifted landward over time.